This is a video about limits. Here we're going to solve question 20. We're looking at the limit as h approaches 0 of, in brackets, 2 plus h cubed minus 8, all divided by h. Here we can see if h is 0, we pretty clearly have a math error. So in this one, what we need to do is try and simplify the top part. In questions like 11, 12, 13, 14, 15, 16, those ones all have polynomials. Here we have a sort of contracted polynomial. It's been simplified into this terms, and we need to expand that bracket out, the 2 plus h cubed. We need to see what that looks like in the form of 11, 12, 13, 14, 15, and so on. So we're going to do that. We'll just expand out that bracket. The easiest way, I think, to do that is to think about Pascal's triangle and binomial expansion. We know that the Pascal's triangle looks like this. We have 1, 1, 1, and we just kind of add on diagonals. And we have 1s on all the corners, so 1 and 1 is 2. 1 and 2 is 3, 2 and 1 is 3. We have 1s on the corners. 1 and 3 is 4, 3 and 3 is 6, 3 and 1 is 4, and then we have 1s on the corners, and we could keep going. This is Pascal's triangle, and it helps us expand out brackets. So this is a bracket, suppose x plus a to the power of 0. This is the 0th row of Pascal's triangle. This is the first one, second one, third one, fourth one, and so on. We can see it's sort of denoted by this diagonal if there was like a 0 there. So what this means is that it helps us find the terms. X plus a to the 1 is x plus a. X plus a squared is x squared plus 2xa plus a squared. These numbers in Pascal's triangle give the coefficients in front of these terms. It's sort of a pattern that we can follow to take a shortcut. For this cubic one, we have this x cubed plus 3x squared a plus 3xa squared plus a cubed. And we could keep going following that pattern all the way down. So what that means for our limit here is that we have the limit as h goes to 0. I'm going to start to expand this out. 2 plus h cubed is 2 cubed plus 3 times 2 squared times h plus 3 times 2 times h squared plus h cubed minus 8, and that's all divided by h. So sort of a shortcut to expanding out that bracket. We can simplify some of these terms a bit. I'll keep using blue. We have the limit as h goes to 0 of 8 plus 12h plus 12h squared plus h cubed minus 8, all divided by h. Here we can see we have some terms that we can collect. We have 8 and minus 8, adding 8 and then taking 8 away. It's sort of irrelevant. The limit as h goes to 0 of 12h plus 12h squared plus h cubed, all divided by h. Our issue is that there's an h on the bottom. If we could factor an h out of the top, that would be awesome. We could cancel off an h on the top and the bottom of this fraction, and we could be left with an equivalent equation that we could actually sub in the value. We can see that we can do that. Each term has an h. So we have the limit as h goes to 0 of 12 plus 12h plus h squared times h divided by h. Since h is not actually going to 0 by the definition of the limits, we're just getting increasingly close to it. we can do this. We have an equivalent equation left. So we have the limit as h goes to 0 of 12 plus 12h plus h squared. If h is 0, then we have this is 12. Oops. Sorry. This is 12 plus 12 times 0 plus 0 squared, which is 12. So this limit is going to approach 12. Basically, any time that we see a single variable on the bottom, and that variable is approaching 0, we have sort of a first principles style limit, and in those we can usually have a bracket on top that we're trying to expand, factor out an h, we're trying to cancel off constant terms, and follow some kind of steps like this, some kind of process like this.